So yeah, today I have Michael from PyroDelta Energy, and we have been discussing in the last few days the new venture, I could say the new application that PyroDelta is doing around these tellurium bismuth crystals or bismuth telluride crystals that are used in thermoelectric devices. And I know at PyroDelta you've been pretty busy lately working on a drone for the Department of Defense heavy lift drone competition, which is going to incorporate a thermoelectric module that replaces the magneto assembly. And part of that is you are manufacturing your own crystals, tellurium bismuth crystals. And so, what we'd like to discuss today is the fact that you are doing this yourself, and it sounds like you're doing it better than the industry standard. And we wanted to just have you discuss that a little bit today.
Hey, Teddy, thank you for having me. Always excited to answer your questions.
I have a lot of them, yes.
Yeah, absolutely. Yeah, just to give you a brief introduction. Um, as you know, PyroDelta is a thermoelectric module manufacturer. We build them from scratch, just like you mentioned. So we start with elements, basic elements, such as tellurium, antimony, bismuth, and we grow our own thermoelectric crystals. These crystals are doped N-type and P-type. And right now, the industry standard for these crystals is just to grow these crystals using a method called the Bridgman method. And the Bridgman method requires that a very controlled heating and cooling process takes place to grow these crystals in one direction, just to make them defect-free. So when they are later cut into cubes, quote unquote, legs that are used in thermoelectric modules are good and in working condition. So this is the industry standard. What
Sorry,
we
Michael,
develop,
and you call these cubes, and then the manufacturers do what they need to do with those cubes. So
that's right.
it's another step that has to be added to the process.
Yes, it is a multi-stage process. It is quite tedious. You first have to grow these crystals, and these crystals are usually sent to another facility to be cut into the desired shape. And then you sometimes they are coated with nickel or other materials or not. So it's a multi-stage process. It is very complicated and requires more than one facility or a very large facility to do everything together.
And these crystals primarily come from China, is that correct?
Yes, the major manufacturer and supplier of these crystals is by far is China. More, I would estimate more than 98% of the crystals available right now in the market, they come from China. To my knowledge, there is a very limited manufacturing capacity in Europe, but my understanding that this is for domestic consumption only.
Okay. And there are concerns around that, or maybe there already are some supply disruptions with China cutting back on its exports of critical minerals.
That's right. From a North American supplier, so we get a very high grade raw materials, and then we turn them into these crystals using our method that's been patented.
And the high purity is important to making
High
these
purity
really.
is important, but from what we found out that the defect-free crystals and the way these crystals are grown matters more than purity. So we try to strive to provide every aspect with its own quality control to make sure that we can produce the best end product possible. And we do that by monitoring each process. So it's not only about the purity of the elements. We need to also create crystals that are very conductive and electrically, and does not conduct heat very well. So that's the challenge with any thermoelectric material. You're always trying to get something that conducts as much electricity as possible without resistance and lower your heat conductivity. You don't want that heat to escape pretty fast without taking the most out of it before it escapes your module. So that's the challenge. And Mother Nature created the materials that conduct electricity very well, also conduct heat very well. So that's the challenge with thermoelectric modules and how to increase their efficiency.
And you had mentioned the other day about the way that they're currently built, the crystals. They, for lack of a better term, the elements in there sort of fight against each other in the typical process.
Yes, because the direction of the material when it's grown into a crystal matters a lot, actually. So if you grow a crystal in one vertical direction and then you cut these crystals into random cubes and then toss them around, up, down, side to side, you don't know which side is up, which side is down. Then you try to arrange them together on the substrate to make them work together in unison. It becomes a bit tricky. And this is a compromise that we are taught to accept in the thermoelectric industry, that there is no escape from that. It is a flow that we need to live with. And in PyroDelta, we were able to break that mold and set free from this little inefficiency and many other inefficiencies to make a practical defect-free thermoelectric module. And the way we do that is by using our capillary casting method, which means that we are growing small crystals to net shape directly. So you don't need to cut these crystals into the desired shape moving forward. You just use them right away, and they are all grown in the same orientation. So we end up with a product that has a much lower resistivity to electricity to flow through it, much lower than anything available in the market right now. And you get a decent flow and even legs. These legs, you can call them cubes if you want. When they are cut, they are not perfect cubes. No matter how sharp is your saw or your cutting device, you will always end up with chips, and you're not going to end up with perfect cubes. But if you are casting the final shape from the get-go, that saves a lot of time, saves a lot of energy and a lot of labor and a lot of expense, but also gives you a perfect crystal in the net shape that you can use on your substrate right away. And to me, this is a game changer in the thermoelectric industry.
Right, right. And you can cast these into any shape that a manufacturer needs. So they're not having to try and fit this into their own stuff. You would give them the shape that they need right out of the box.
Yes, that's one advantage, and I think that makes us very special, is that you can come to us and we will develop your prototype within 1 week. You will have the shape that you need, and then once we get the approval that works for you, we will start manufacturing them in bulk. So that's something that's not available because of the tooling costs with other methods. So if you approach a vendor in another country or a big supplier and you try to get a specific type of cube, most probably you will end up with a negative answer, or you will have to place a really large order to justify the tooling that goes beyond that. So for us, we're not constrained by tooling. We can change the shape as much as we want, as much as the customer wants, and to fit their needs, and create a custom thermoelectric device or custom thermoelectric legs if the customer wants to create their own modules.
Okay, and are you able to show us a sample of a mold or I guess
Yeah. Give me one moment. So allow me first to show you what's available out there in the market. These are the ingots imported from China, and these are the ingots of bismuth telluride. These are crystals, actually. It looks like a piece of metal, but it's actually a crystal grown, from the bottom up, just to give you this defect-free, no pinholes, nothing. It's just a shiny, good crystal. And they are grown using the Bridgman method that I explained. So this is the industry standard right now. So what you do with this is that you cut it into very small cubes, like about 1 millimeter by 1 millimeter. And with that, there is a lot of loss in the form of sawdust and defects and all of this. But our capillary method, we actually create our own molds depending on the customer needs. Let me show you some of our molds. So this is an interlocking mold. You can see how fine that is.
Yeah.
This is done in 1 millimeter copper. This is all done in-house. And this is another mold also that the plan is to create crescent shape thermoelectric legs. And the way it takes place, it goes through these small cavities. I don't know if the camera can capture that. It goes through these small cavities, and then it fills this void here, giving you the final net shape of the thermoelectric legs. And let me show you an example of one that's already been casted. So here you have the crystals already embedded in the mold, already after being casted. These are bismuth telluride, the silver parts here. These are bismuth telluride casted already in a copper mold. And the way we get defect-free castings in these is that there is a 0.4 millimeter entrance for the metal to flow in. So this way, only one crystal can form inside this cavity. And we have our own method that's been patented that helps us make sure that the molten metal flows in a way that is controlled, and it flows from a hot section to a colder section, forming these tiny crystals formed in the same direction. So when they are placed on a substrate, they don't fight each other, and we get very good low electrical resistivity between these legs, which is something unheard of in the thermoelectric manufacturing world. I think we've really changed a lot in this field.
So there's you're talking about a few different advantages here. One is the manufacturer isn't having to do all this to get this right shape and losing some efficiency of the module in the process, but also they don't have to do this themselves.
That's right. So it's really important that we can give this flexibility to the end user, because the end user look at the thermoelectric devices and all they see is square cubes. So they have to design their devices around squares and cubes and stuff like that. But what if they want a tube, a thermoelectric tube that generates electricity at both ends? If you pass half fluid inside while you're cooling it from the outside, for example, and this is your delta, this is your heat differential, and you get electricity at both ends. So thermoelectric devices need to be more flexible, need to be more adaptive to technology, and give engineers and manufacturers the ability to utilize them where they see fit. If they are just being cubes and made in a very specific way that suits the manufacturer or the bulk supplier, then it really constrains engineers and designers to utilize thermoelectric materials in their applications. And we're giving them this flexibility.
And so the tubes is something that is new in the industry, correct?
That's right. I mean, it's been tried by several companies before, but because it was very tedious and it's very expensive to manufacture thermoelectric material in the form of rings or tubes that can be constructed into a larger format thermoelectric module, it becomes cost prohibitive and they just abandoned the idea until we came up with our own capillary casting method that enable us to create these crystals in any shape or form that we desire, defect-free and very high quality crystals. So if you want them in semicircles, one half is N and the other half is P, for example. N and P refers to the dopants used in these materials. So there is bismuth telluride N and bismuth telluride P. And when you put these two together, you have a thermoelectric module. And if you want to divide your circle into, let's say, 8 segments, 4 segments are N, 4 segments are P, and then arrange them in series to create these circles and tubes, and the sky is the limit basically on how you want to design these with this casting method and the way we grow crystals.
And the tubes is one reason that the AI industry with the big data centers are very interested in this, because it allows you to take the waste heat from an AI data center and generate power for whatever you might need it for, I guess.
Yes, absolutely. And some people argue about the efficiency of thermoelectric devices. If they are really good, they can reach 11, 12, but they are solid states. They don't make noise. They don't need lubrication. They just stay there where they are. This is just wasted energy that was going to go into our lakes, into our rivers. And we are just using some of that. If you can recoup 11% of your wasted heat that's being dumped into our rivers, that's something big. It's economically viable. And it doesn't need maintenance. You just install it once, and it just keeps generating electricity for as long as you have it.
All right, and so there could be many applications where it may not be quite this broad, but anybody that generates hot liquid in any sort of process could use.
Yeah, absolutely. Our tubes can be integrated into their cooling system. Just like as a part of your tubing system, it will not restrict your cooling flow or add any obstacles in your system. It will just generate an additional DC current that can be used to run your sensors, to run your anything that you can think of, to use that excess heat or excess waste to make your process more efficient and more environmentally friendly.
And this is the same process that you are working on that could potentially replace alternators in combustion engines.
That's right. So what we built basically, just to showcase how rugged and how efficient our thermoelectric modules compared to anything available in the market, we create these heat sinks and heat exchangers basically. So any device that needs cooling, whether it's an engine that needs to be cooled, or and even a data center that needs cooling as well. Any device that uses this technology, we created these thermoelectric radiators, thermoelectric heat exchangers. So basically, as long as you have hot liquid passing through these heat exchangers, and while it's being cooled at the same time, passively or actively using a fan, or even if you're leaving it in a cold bath of water, or if you have a lake or some ice somewhere, that if you bury it in ice, that will still generate a lot of electricity. So like I mentioned, the beauty of this is that it's maintenance free. You don't need to clean it like solar panels from ice. Actually, if ice drops on it and covers it, that makes it even work better. So that's one of the advantage of it. It's solid state. It's reliable. It's just a workhorse in the background. You will forget that you even installed it.
I remember one of your demonstrations where you had uh, poured ice water
Yes.
onto the device, and it generated electricity. And then I believe I don't know what you used for the heat. Maybe it was just your hand, but I remember. So you showed that both, as long as there's a temperature difference.
Yeah. That's how all thermoelectric devices work. They work on heat differential. So it doesn't have really a preference. As long as there is a heat differential, it will work. And the big catch here is flexibility, the shapes that you want to create, how fast you want it, and it has to be cost effective. And the most important part is durability. You want
Yeah.
these things once they are installed somewhere and embedded in a system, let's say on the top of a mountain, or you put them somewhere that you don't want to go and change the battery or send someone somewhere like a chimney or somewhere that's dangerous. You don't want to send someone all the time, for example, to change a AA battery on the top of a chimney just to be able to get your readings, right? So you just want to set it and forget it kind of thing. So this is where thermoelectric devices shine, with remote sensing and all these low energy requirement sensors that are placed in places that's hard to reach. This is where we shine. And you want to put a thermoelectric module that will last for 10, 15, 20 years untouched with no cracks, that can tolerate a lot of heat cycling. So if you grab any of these cheap thermoelectric devices from the market, um, it won't last for like a couple of weeks, and then cracks will start to form, and it will lose its ability to generate electricity from heat differential. And this is where we shine because our crystals are grown and used right away because it's a net shape.
And I remember too that these can withstand much higher temperatures than what's available on the market, or at least without some very expensive processing. I know that NASA uses these, but they're very expensive that are able to withstand these high temperatures. And you're bringing this down to pretty much anybody could afford this.
That's right. So because we have an absolute control over how we put the ratio of the materials to create these crystals, we can tailor it up to your heat temperature zone. So we can, let's say, add a little bit more antimony, or I don't want to get into the material science because it gets boring, but
Yeah.
we can add other materials that makes it withstand higher heat and be optimal for this range. So one of the questions we ask our partners and collaborators and people who want to work with us, what is your temperature range? What are the temperature range your equipment operate on? And based on that, we come up with the sweet spot of ratio between the materials to be able to custom tailor a thermoelectric material that can work for this application. And after that, we start casting them in the shape that the customer needs. So nobody provides this right now except PyroDelta, and I think this is where we shine.
Okay. And you had mentioned about these sitting somewhere and working for years and years without anybody having to go in and, as you said, change batteries or things like that. Um, solar power. So one of the problems with solar power is, of course, it's not generating any energy at night. And I believe you've discussed the possibility of using these devices on solar panels so that they can generate electricity when there is not sunlight hitting them.
Yes, so I think they really complement solar, even existing installations, so they can be retrofitted at the back of solar panels. So um, one of the things about solar panels that people don't discuss much is that solar panels don't like to be heated too much. So they
Mhm.
like the sun, but they like the sunshine, but they don't like the heat, just like the rest of us, right? So solar panels basically they get very hot, and when they get hot, their performance starts to drop. So it's been tried before. It's proven method is just to improve your solar panels. You can put a backer of thermoelectric devices at the back of it, and this way you're getting a heat differential between the solar panel itself and the shaded area behind the solar panel. So this heat differential can add to the efficiency of the solar panel in general, and also generate electricity during the nighttime. So if it's being cold and these solar panels are close to the ground, just the heat radiating from the ground in the back of the solar panel and the wind blowing on the top of it, this creates a heat differential as well. Everything counts when it comes to electricity, and when we have the ability to manufacture these in bulk in films of thermoelectric material that can be a backbone of existing existing photovoltaic panels, that just adds more value if it's done correctly and in an economic way. And we have the recipe for that.
So that just opens up, it seems to me, like an unlimited amount of options for anybody that is generating heat in like a greenhouse. Or I mean, there must be, I mean, I can't think of them now, but there must be many, many places that could have supplemental power just because they're generating heat.
You're right. I mean, we've been approached by a lot of genius engineers and even DIYers, and a lot of the maker community tried to reach to us, and we really appreciate all the feedback and constructive criticism and everything. Everything we do is based on science and testing. We're not blowing things out of proportion. There are limits for thermoelectric technology, but right now we have the most effective and cost-effective way to deploy these devices. But it's very important for us to put our devices in high-value applications. So that's why we are not mainstream right now. We are doing pilot programs, just like what you mentioned when we started our conversation with the DARPA Lift Challenge. No, we're not a drone manufacturer, but we know the value of our modules or our thermoelectric heat exchangers in a drone, because they are pretty light and they can recoup a lot of wasted heat from the exhaust of a combustion engine. So anything that's very light and can provide more energy than that offset its weight on a drone, that's absolutely a game changer in that field. So we're excited to participate in the DARPA Lift Challenge, and yeah, we're looking forward to it.
Yeah, and I know I've seen some of the work you're doing on this drone for the DARPA Lift Challenge, and just removing the magneto assembly, it has, I mean, that's a significant weight advantage.
Yeah, so just to clarify, the magneto that you mentioned is basically a generator. And it's called magneto, it's called a generator. I just wanted to give another name for it for people to be familiar with it. But it's basically a small alternator or generator or magneto that provides this needed power for the battery on board of a combustion engine drone. So the battery, no matter how big it is, or no matter how small it is, it still give you this weight. So our goal was to replace that battery with a heat exchanger paired with a capacitor bank that generates enough electricity to run all the electronics on board the drone. And this saves weight, and it saves energy, and it provides a lot of energy and give all this energy to the propellers.
Yeah, it's not using part of its power to turn the magneto assembly.
Yes, that's right. So it's not a parasite. It does not work as a it's not taking any of that energy. So all the energy is going through the engine straight to the propellers, and we're just using this wasted heat from the exhaust to generate enough electricity for all the onboard electronics. And in this application, every ounce, every gram counts, and this is where our technology will shine.
Now, Michael, one thing you had mentioned to me before was that your method doesn't use soldering, or it's more efficient. Can you explain that a little bit?
Yeah, so because we cast our own um, legs, our own crystals, we actually cast them. We have two solutions for that, and they both work phenomenally well. The first one is to basically embed a copper tap inside the crystal while it's being grown. So basically, the crystal is being grown around a copper tap, and this is how you get your connection. It's embedded in molten metal, grown as a crystal, rather than just having a piece of copper being soldered on it. And then using solder, solder is a very low melting alloy, and once the module is exposed to cycles of heating and cooling, it starts to crack and just disintegrates, and the module becomes useless. So I think in that regard, uh, our modules are superior to anything available in the market, having these embedded connectors or embedded tabs already inside the crystal.
Okay. So, Michael, if a thermoelectric module manufacturer or an end user, whatever, would wants to learn more, how would they get a hold of you?
They can reach to us through our website, www.pyrodelta.com, and we'll be more than happy to answer questions, and we can explore future collaborations.
Okay. Is there anything else that you can think of that would help a manufacturer understand this, or other ways to use it? Anything else that we might have missed?
Yeah, I just want to address engineers, designers, makers that thermoelectric devices are not limited by shape or form or temperature range anymore. These have become very customizable using our process and very obtainable, and we'll be more than happy to work with any designs.
Okay, that's all very exciting. It sounds like you're moving thermoelectrics into a new era.
We sure hope so.
Okay. Thanks, Michael.
Thank you very much.